Yes, now we have 3DCS integrated with SOLIDWORKS. We come in as an add-on workbench with two tabs. One is the 3DCS Variation Analyst Home tab, which covers all the basic functions like feature creation, model creation, analysis, and the reporting tool. And then we have a 3DCS add-on tab where we have the mechanical, complaint, and AAO functions. So now then we have a 3DCS model navigator tree, which exactly resembles the SOLIDWORKS tree here.
The four main inputs to a tolerance analysis model is the CAD data, moves, how it goes together, tolerances, part variation, and measurements, what we want to measure.
So I got a patient lift model assembly here. You can see how the parts are deviating. That's because of the applied moves and tolerances that I have added to the model. So let me go ahead and show the measurement. Here I'm going to need to measure the angle between these two rods here. The one main thing here is I've used a multi-stage assembling process which assembles this plate and rod to a fixture tool, which in turn assemble the whole sub-assembly into the top level assembly to the spine rod. So let me animate through. You can see how the plate goes into the fixture tool first, followed by the rod. This happens on the right side. So now that's the sub-assembly move. Now I'm going to assemble this whole sub-assembly into the spine rod. So first thing is placing the spine rod in position and then bringing in the rod there. And we have a pattern move here at this stage which aligns the whole pairs of the plate and this spine rod. And when you look into the move list, for an example, I've used a combination of both analyst and mechanical moves so that I can cover both and show you a model can be built with any combination. So the other set of moves which assembles the rest of the parts would be all mechanical. So I'm fixing the spine bar, putting in the piston rod, the bar, then goes the arm, and finally that's attaching. And also the main purpose of having the mechanical move here, this upper rod is free to rotate up and down, and that's a motion. So that's why I've used a mechanical move combination in it. So that's the GD&T. And this GD&T can be created in two ways. One, it can be done inside 3DCS using our GD&T function, or if this part already have embedded GD&T information that was created inside SOLIDWORKS, we can pull that inside 3DCS. So this GD&T was created using MVD dimension here. I've used these functions to create the GD&T on this part. So you can see these parts have the tied up GD&T. Now coming back to the assembly, I'm just going to show you the function under update model, which is called update GD&T. So just by clicking this and selecting the part from which you want to extract the GD&T, it pulls up all that and gives you a message, okay, these many GD&Ts was extracted from that part.
So at this point, you don't see any deviations on the screen. The computer is applying tolerances internally to the piece parts, building it, checking that measurement, and then it's collecting that data for 2,000 times.
One go. So the benefit of having the table view here is you can see all the measurement results in one single display page. So the angle between the bars is the measurement that we're gonna check here. And if you want to see the graph view of this measurement, you can just simply double click and that will pull up the graph view for that measurement.
Then this is, this result is telling you the nominal angle, the min and max angle, the range of the angle variation, and the causes of variation at the bottom.
I did only changes to the move pattern, but there's no changes in the part level tolerances. So I'm using the same tolerance in the model. And once the results are up, we can compare the results between the process 1 and process 2, see which process is most suitable.
So this is an example of you can improve your process by adding tooling. Of course, that's a capital investment, and it may increase the assembly time. So it's going through a range of motion plus tolerances. It's hard to see because of the motion, but there's going to be a variation on that with the motion.
So now that we went through these process, We created tolerances, we added moves, we took the results. So now we have all the information in the model that we wanted. The next step is to take a report, a final report for all these information. This is how the report looks like. This is the
Basically, once this model is done, with the push of a button, you can get a report that can document everything that's in the model, as well as, the results, the measurements that you were wanting.